Okay, we're going to continue on. We are still on chapter 14. But I believe last time we finished up basically what I call sort of part one of chapter 14. And now we're going to get into part two. We do have a quiz again, a reminder on Tuesday on the first part of chapter 14. So that should be everything that's covered in the part one of chapter 14 notes and where we finished last time, which I think was doing some polyprotic acid calculations. So part two, which is a lot of times in its own chapter here of chapter 14, is going to get into all the fun hard stuff. Yes, so we are, as we talked about previously, we're kind of going up the hill on the roller coaster, and we are now at the hill. So in terms of the toughest part here for a lot of students in this class. So in this part of the chapter, we're going to talk about buffers, and we're going to talk about titrations, and that should keep you busy, I suppose, in this part of this chapter. All right, so we're going to talk really about acid and base equilibrium now that we sort of talked about, obviously, in the first part about acids and bases. And one of the first things we're going to talk about is, oh, there it is. We're going to talk about the common ion effect. And the idea of the common ion effect is a really big sort of principle in this part of the chapter, especially as we'll talk about buffers. It is essentially what a buffer is the sort of effect of a common ion effect. And it has a lot to do with, what happens in a particular solution. So when we have a common ion that is present, what it essentially will do is it will suppress the ionization of a weak acid or weak base. So essentially, if you have a common ion, it's going to basically keep in the idea with acids and bases, it's going to keep your acid together and it's going to really keep your weak base together and not allow it to sort of break apart. So, for example, if we just go back here, it's probably why I had all those empty spots. If we take a look at a common weak acid that we see a lot in this chapter, which is acetic acid, and acetic acid is a weak acid. Once again, I do know, by the way, again, acetic acid is a weak acid because uh, it has a Ka value, but more importantly, it's not one of those six strong acids that we've been talking about. And again, by process of elimination, you have an idea that this should probably be a weak acid. Since it is a weak acid, it's going to set up our favorite thing ever, which is an equilibrium. And as it dissociates, it will dissociate in this case into acetate and H plus. So if we had just a beaker of acetic acid sitting there, a little vinegary, we will have basically this equilibrium set up in our solution, arrows and all. You could probably see them in your solution there, floating around. And we have basically this equilibrium set up. Now, if we take this same sort of beaker, our same solution of acetic acid, and we put the acetic acid, say, into the beaker, and along with it, we put in something like, say, sodium acetate. So if we take something like acetic acid and we dump in there something like our friend sodium acetate in this case. Now, out of these two things, we have a weak acid, and we really have, as we talked about earlier on this chapter, we have a salt, right? And between the two of them, only one thing will set up an equilibrium, and it's going to be the weak acid. So out of the two, this guy is a weak electrolyte, which means it will set up that equilibrium. Thank you very much. This salt is actually a strong electrolyte, which means it's going to completely break apart into its ions. So in terms of an equilibrium being set up, we actually will, in this case, have the same equilibrium as above. We will have our acetic acid setting up its equilibrium. In that beaker, just like we have above there. But the difference in this particular case is we have added some sodium acetate with it. And that sodium acetate, which is a salt and a strong electrolyte, is not going to stay together when it goes for a swim. So if we took our sodium acetate and dumped it into here with it, it is going to 100% break apart into sodium ions and acetate ions in this particular case. And the result of that is, as you could probably see, we have the name of common ion there. The common ion between those two is the acetate ion. Yeah. So we have an acetate ion that's in common with our equilibrium that's set up. And our good friend Le Chatelier's principle will tell us that essentially I am now going to be adding more of my acetate. That's going to cause the equilibrium to do what? It's going to shift. Which way will it shift? It is going to shift to the left in this case, because in this case, by adding the sodium acetate, you're adding more acetate to that equilibrium. Le Chatelier's principle now says I have more products than reactants, and we're going to shift away to the reactant side. Any questions on that? So that is what it means when it says it prevents the weak acid or even a weak base in the same sort of situation from ionizing. It's kind of pushing it back to want to stay together. Now, what is the actual effect of that on the solution? Well, if we're talking about pH, would I expect the pH of my acetic acid solution by itself versus my acetic acid solution as a sodium acetate? Which one should have the lower pH? Is it the acetic acid by itself, or is it the acetic acid with the common ion? Which one do you think should have the lower pH? The acetic acid by itself would have the lower pH. And the reason for that is when we have the common ion, it does shift the equilibrium to the left. What does that mean about our friend H plus concentration? Is it going up or going down in that case? The equilibrium shifts to the left, the H plus concentration should go down. The reverse reaction is happening. So what we're going to see here is our H plus concentration is going to go down. And that means the pH here will actually go up, right? Since pH is equal to minus the log of the H plus concentration, right? So because this equilibrium is going to shift to the left, it's going to mean that you're going to have less free H plus in the solution. And that free H plus is what affects the pH of the solution, right? So if we have less H plus in the solution, we would expect the pH to be higher than just the acetic acid by itself without the common ion being present. Will it become basic? The answer is no, but it will be higher in comparison to the acetic acid's pH. And it's because, again, you have less H plus freely floating in that solution because of that shift in equilibrium that occurs. Question on that. That is really the basis of common ion. It's that principle right here. And as we'll talk about, that's really the principle of what buffers are and how you make a buffer and how it works is a common ion type of solution. Any questions on that there? Now, this happens with weak acids, as I mentioned before. It also happens with weak bases. It's the same idea. When you have a weak acid or a weak base, your ions are going to be on the product side. So again, having a common ion is going to push everybody to the left and keep everybody together. So because of this effect, it does, as I just mentioned there, affect the actual pH of the solution when a common ion is present versus when it is not present. And it does affect, obviously, the overall pH of the solution. So if we take a look at an example here, and we got two parts here, part A and part B, let us calculate the pH of part A, which is calculate the pH of a solution of 0.2 molar acetic acid. The Ka value down here for acetic acid is 1.8 times 10 to the minus 5. So for a moment here, just work on part A and see what pH you get. Okay, let's take a look first one, see how you're doing. So on the first one, we want to calculate the pH of a 0.2 molar solution of acetic acid. Again, we have a Ka value given to us, so we definitely do know it is a weak acid. So really part A here is just a weak acid problem like we did in the earlier part of this chapter. So we have 0.2 molar acetic acid. And again, we have a Ka value of 1.8 times 10 to the minus 5. So just a basic weak acid type problem, Ka type of problem. So we're going to take our weak acid here and we're going to break it apart into H plus and acetate. We have an initial concentration of 0.2 and 0 and 0. Our change is going to be minus x, plus x, and plus x. And that means here 0.2 minus x, x, and x. Any questions on the table so far? Going to go into our Ka expression here, which like normal is going to be our products over our reactants. And putting that in, it's going to give us x squared 0.2 minus x is equal to 1.8 times 10 to the minus 5. Here it is a small value k, so we can try our assumption. We do want to assume x is equal to 0 here. That's going to give us x squared divided by 0.2, 1.8 times 10 to the minus 5. Again, I'm going to multiply followed by a square root here. And just going to get us something. So 1.8 to the minus 5 times 0.2, a little square root action. And that's going to give us an x value here, 0.001897. We're going to divide it by 0.2 times it by 100. And I think we are good in this one. We're like 0.9% maybe, or even less than that, I think. So check is good. Again, in this case, X does equal the H plus concentration, which is what we need for our pH. So our pH here going to be negative log of 0.001897. It's going to give us kind of an opening pH here for this one of, I probably should hit the right number there. Looks like it maybe 2.72. Looks like a winner. That is an acidic pH, which is good since this is a weak acid. Again, if you got like a basic pH, that probably would not be so good, I imagine. Yeah. Any questions on that there? So this one here is obviously not a common ion situation. It's just a weak acid situation. So let's take a look at B, which might be a common ion situation. And we'll talk about how we should go about the calculation here in B. So we have the same solution of 0.2 molar acetic acid, but in addition to that, we're going to add 0.3 molar sodium acetate to it. So that is, as we talked about earlier, going to cause a common ion effect to occur. And let's see how we handle that in calculation form. So again, we still have our 0.2 molar acetic acid as we did in part A. We're going to dump in there 0.3 molar sodium acetate. And we still have the same Ka value of 1.8 times 10 to the minus 5, which goes with our weak acid. Again, recognizing what we got going on here, weak acid, and again, a salt, which is again a strong electrolyte. So as I mentioned before, the only thing between these two things that are going to set up an equilibrium is the weak acid because it's the weak electrolyte. So we do need to do an ice table, and we would do it based off of most likely here our weak acid breaking apart. And we'll do that. Now, when we get to our initial here, we have 0.2 molar of our acetic acid. We have 0 of our H plus. And now probably the most important thing ever, and the thing that people screw up on all the time is answering this question. Is this 0? It is not 0 because if it was 0, I'm just redoing the same calculation I just did on the last slide, right? I'm just doing the weak acid. It is not 0 because in this beaker, along with the acetic acid, right, that's in there, is this guy, right? We have some sodium acetate that we put in there. And sodium acetate is a strong electrolyte, which means unlike acetic acid, it is not going to set up an equilibrium. It's just going to simply fall apart into its ions, sodium ion and acetate ion. And the common ion here, obviously, as we talked about previously, is the acetate ion. And we need the concentration. So that if that is 0.3 molar, it is a 1-to-1 relationship between those two. The ion would also have a concentration of 0.3 molar. And that is where that initial 0.3 comes from. The salt here, let's break it apart, and supplying basically a certain amount of acetate in the solution. Question. Yeah. If you're talking about the concentration part, correct. So like if that just hypothetically there was a two, it broke apart into two acetates, the concentration would be twice the amount of the original ones. Yeah. So it's kind of similar. I think we came across that when we did earlier on in the chapter where we had something like I think it was calcium hydroxide, and we wanted the hydroxide concentration, and that breaks apart into two hydroxides. So whatever the whole concentration of calcium hydroxide was, you have to multiply by two to get the hydroxide concentration. Yeah. Other questions? So that is again probably the most important thing in this table is that number because again, if you just zero it, which is a very common error people make because at this point we're kind of used to just zeroing out everything on the right hand side, so we kind of automatically do it. Again, you're just kind of repeating the same calculation we did before. The rest of the table here is going to be pretty identical to all the other tables, thousands of tables we've done. Minus x, plus x. Maybe it's not thousands, it just feels like thousands, but we'll go this way. And we'll go 0.2 minus x, x. And also, second big mistake people make, this is an addition on this side, it is not a subtraction. And people are always used to, at this point, subtracting x. So again, they kind of go automatic and subtract on that point. So again, it is a plus x on that situation. Any questions on that table? All right, so just like we did on the last one, we're going to go into our Ka expression, which is really the same expression as H plus over acetate divided by our acetic acid here. So that's going to get us an x, a 0.3 plus x divided by a 0.2 minus x equals our 1.8 times 10 to the minus 5. So just like we did on the last one here, we're going to assume x is equal to 0. Once again, that's going to get rid of just these x's here that we're adding or subtracting. So that's going to reduce this down to basically x times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. We're going to multiply that to the other side and then divide that guy, right, afterwards. And if we do that, so we're going to go 1.8 to the minus 5 times 0.2 divided by 0.3. That's going to give us a lot of zeros. That's going to give us the next point. 1, 2, 3, 4, 1, 2. Like always, right? Got to check it. So we'll divide it by the bigger number there and times it by 100. And usually if one works, the other one's going to be okay too. And we're also good here. So check is good on this case. That means once again, when we go to our table, we can see that X does equal the H plus concentration. So this is going to equal the H plus. And now we could get our pH by going minus the log of whatever we got going on there, 12. And minus the log of that. Gives me an error because I'm logging after my number. Let me try that again. Let me log first and hit the right number there. All right, a 4.92 looks like it. Any questions on that calculation? So let's talk about a couple of things that we just talked about in terms of common ion. We obviously have a common ion effect happening here. When we compare the pH of the acetic acid by itself, which was 2.72, to the pH with the common ion, the one that's higher is The one with the common ion is the higher pH, right? The one without the common ion is the lower pH, because in this situation, we have no Le Chatelier's principle happening, right? In this situation, we do. Again, because we have the addition of this guy is going to cause the equilibrium to shift this way, and that's going to lower the free H plus in the solution. And that results, as you can see here, a higher pH in comparison to just the weak acid by itself. Any questions? Good. All right. So you obviously can work out these problems with an ice table like we've done before. And there is a couple of things that does happen because of this common ion effect, which is basically keeping everybody together. What happens is because the equilibrium shifts to the left that keeps everybody together, the change that occurs from beginning to end actually ends up being relatively a small change. So if we take a look really here at our table, our change in this case is our X value, right? And our X value here is pretty small. So if you were to take the X value that we got in this common ion and put it back in up here, kind of what we saw when we did our polyprotic acids, when you put that number back in, we pretty much are going to stay at the same number, right? It's not going to change. So in this case, we basically had 0.2 that we started with, and we kind of ended with 0.2 at the bottom, a little less. And we started with 0.3, and we had a little bit more there at the end, but not significantly more. We basically have the same numbers. So in situations like this, when you have a common ion effect, and really when you have a buffer, you don't necessarily have to use an ice table. You could do a bunch of rearrangements of equations, and you could get everybody's favorite equation, which is the Henderson-Hasselbalch equation, David Hasselhoff equation, whichever equation that is there. That is the pH is equal to the pKa plus the log of the conjugate base over the acid. So the pH here is going to be our pKa value plus the log, basically the concentration of the base over the concentration of the acid, where the pKa value, as it shows there, is minus the log of the Ka value. So you could actually just bypass the ice table if you could recognize this is what's happening, and you could go right into that formula and get the pH. Now, I personally am a fan of that equation, and I personally will use that equation, the Henderson-Hasselbalch equation, in all situations. It could be sort of an acidic buffer, a basic buffer, a neutral buffer. You can really use it in any situation. You will sometimes see people use a version of the Henderson-Hasselbalch equation, which does not calculate pH, but calculates our other favorite P guy there, POH. And the POH is equal to the pKb plus the log of the acid over the base. It is flipped. And the pKb is minus the log of the Kb value. So sometimes people will use this equation, especially in a basic sort of buffer situation. I personally don't see the use of it in most cases because in most cases you're asked to calculate the pH. So why not just go into the Henderson-Hasselbalch and calculate the pH and be done with it? But you could do this, but you have to remember that you will end up with the POH, which means you then need to subtract 14 to get yourself to the pH. So again, you might as well just go into here and just get the right thing that you're probably looking for in most cases. Because like I said, probably 99 times out of 100, you're looking for pH rather than POH anyway, so might as well go in there. But that is a legitimate one. But if you do choose to use it, you need a pKb, and this one is flipped in the normal Henderson-Hasselbalch equation. But speaking of pKa and pKb, those are some helpful numbers because there is a nice relationship between the two that if you take the pKa value plus the pKb value, it equals our lucky number of 14. Kind of like when you take the pH plus the POH, it equals 14. Same deal, basically, in this case. So if you happen to, for example, only have the Kb given to you, you could calculate the pKb, subtract 14, and now you got the pKa that you could go into your Henderson-Hasselbalch equation with. So again, it gives you a little flexibility in terms of how you can calculate some of these things along the way. So my vote is probably always go with this one because that gets you probably what you're looking for in most cases, and you don't have to worry about not converting or thinking that's the pH and stuff like that. Any questions on that? Yeah. Sounds like the lab. Is this a hypothetical? But I don't think it is a hypothetical. You will have to in some cases look up the values, and I think specifically in that lab you do have to look up the values. I think they just give you a list of the stuff, so you will have to look it up. But I won't say that. Yeah, so it's possible you could have a weak acid or weak base that is derived from a polyprotic acid or something like that. That you may have to find the right if you're asking one, two, or three value for Ka or not. But yeah, you would have to. So, for example, and we'll talk maybe more about it when we get to titrations. But if you had something like, say, phosphoric acid, right, which obviously has three hydrogens and it has three Ka values, right, Ka1, Ka2, and Ka3 that we talked about. That means it also has three pKa values associated with each of those that you could calculate. And that you would again want to choose the right one if it was a situation where maybe you're using something from the Ka3, you would want to use that perfect one as well. And that's why, as we'll talk about with titrations, you actually get three equivalence points if you do a titration with one of those, one for each of the hydrogens that come off. Not that you would probably be able to see the third one. It probably is very hard to see, but as well. All right. So we have our Henderson-Hausbach equation. Now, a couple cautionary notes on this formula, which we haven't seen a formula in a while, right? So people see a formula and go, cool. Anytime I have two numbers, I'm just going to lay it up into that equation. You don't want to do that because you probably will receive an X at some point when you do that. Yeah. So it can only be used really for a buffer situation, which is a common ion situation. So if it is not a buffer, you should leave Henderson-Hasselbalch there on the side and you should not use it. It is a very specific equation for a very specific situation. And very commonly, people, again, like I said, they end up with two numbers ago. That's like the only formula I know. And it's got two number spaces. So I'm just going to throw it in there. So you don't want to use it in the wrong situation. Has to be a common ion and hence has to be a buffer situation. Now, we did have that situation if you think about the problem we just did, which was this one here, where we had our 0.2 molar acetic acid and our 0.3 molar sodium acetate. So that's the one we just did with the ice table. And we had our Ka value of 1.8 times 10 to the minus 5. So this is a common ion, and one of the ways you can recognize sort of a common ion and really a buffer, by the way, is by those two things being related to each other by the Bronsted-Lowry definition of 1H plus. So again, acetic acid is going to break apart, obviously, as we talked about, into H plus and our acetate. And our sodium acetate being our source of acetate gives us our common ion. So we could skip the ice table, go right into our Henderson-Hasselbalch equation in this case. We do need to calculate the pKa value, which is minus the log of our Ka, which is minus the log of 1.8 times 10 to the minus 5. That's going to give us a 4.74 for our pKa value. We then will go into our equation, 4.74 plus the log of our base. Also important to make sure you get the right thing on top. Which one's my base? What is the first thing called here? That is acetic acid. Probably not my base, right? Because it's called an acid. So this would be my base. Yeah. So you want to make sure that you got this guy, right, over this guy. How do you know which one's the acid? Definition of an acid is somebody that could donate a H plus. Acid typically has one more hydrogen than the other guy. Yeah. And also the base or the salt in a lot of cases has some type of like sodium, potassium, spectator ion hanging out there. And again, if you kind of compare this to this, one less hydrogen than this guy, right? So again, you kind of know that's the acid. All right, so we pop that in there. We do a little math risky here on our calculator. A little log action, a little adding of 474. Gonna get us the 4.92. Dare I say that looks like a familiar number because I feel like I saw that right about here with my ice table, 4.92. Yes. So this demonstrates two things for you. You could always roll with the ice table. Yeah. So you could always roll with the ice table, even on these type of problems. Uh, the key is again, make sure you have that initial concentration on the other hand, on the other side. But again, if you can recognize it is a buffer situation, roll with the Henderson-Hasselbalch so you don't mess up the ice table by not putting a concentration on the other side. Yeah. But you can do either one. They both will give you basically the same answer. Any questions on that there? Okay. All right, so let's try one here and see. Let's take a look. There it is. What is the pH of a solution that contains 0.3 molar? I'm going with formic acid. How's that? And 0.52 molar potassium formate. Sounds good. Ka equals 1.7 times 10 to the minus 4. I could be right. Maybe I'm wrong. I don't know. I was a history major. I minored in English, though. That's okay. Good news is chemistry was my worst subject. It's reassuring. I know it's okay. All right, let's take a look. So again, we have 0.3 molar formic acid. I know that's a weak acid because I have a Ka value. I also know that's the acid because it's got an extra hydrogen. This one's missing, by the way. This also has the potassium in there, which tells me this is more like a base type situation happening. And in this case, if you recognize it as a common ion, you could definitely go into the Henderson-Hasselbalch equation, which would be pH is equal to pKa plus the log of the base over the acid. And in this case, our pKa value will be minus the log of the Ka, which is 1.7 times 10 to the minus 4. That's going to get us a pKa value here of, it's like 377, we'll call it. So the pH will equal 3.77 plus the log. Once again, this is going to be our acid. We're going to go on our base, going to go up on top. Divided by our acid, which will go on the bottom. And that's going to get us 0.52 divided by 0.3. Going to take the log of it, going to add it to 3.77. Going to get us a 4.01 pH in this case. First off, any question on that calculation? Again, if you chose, which is perfectly fine, and wanted to do more of an ice table approach, again, the only one setting up to equilibrium is going to be the weak acid here. So you would just do it like a kind of like a Ka problem and just have your acid break apart. And initially we would have 0.3, we would have 0. And as we talked about on the last slide, there's the important one. We do need to get the 0.52. That's going to be supplied by the potassium formate in this case. The rest of it is going to be minus x plus x plus x. And you're going to go through your normal solve for x in this case. Again, plus x here. And you're going to solve for x, which will equal, in this case, the H plus concentration. And then that could go into your pH. And you should end up, obviously, with the same answer there. Any questions on up there? All right. So a common ion really is a buffer. So let's really talk about what a buffer is, how a buffer works, the funness of buffers. So a buffer is a solution, first off, that is made out of a combination of basically two things. It is either a weak acid and what is referred to as the salt of its conjugate base. Or you could have a buffer that is made out of a weak base and the salt of its conjugate acid. What is the relationship between those two things? A weak acid and its conjugate base, or a weak base and its conjugate acid? It is the Bronsted-Lowry definition of 1H plus difference. So 1H plus difference between them is what is part of the buffer. A buffer works because it has both of those things in there to begin with. You cannot have a buffer that is made of a strong acid or a strong base. So buffers, you cannot have either a strong acid or a strong base that is making up the buffer. Not to be confused, as we'll talk about, you can make a buffer from a reaction of a strong acid or a strong base, but the strong acid, strong base is gone, and what you're left with is the buffer. You kind of make the buffer that way. But the buffer itself has to be a weak acid in its conjugate base or a weak base in its conjugate acid. And again, they both need to be in the solution to begin with. What is a buffer? First misconception about a buffer is people think it has to be a neutral solution, and it does not have to be a neutral solution. So you can have a buffer at any pH you like. You can make a buffer at any pH along the pH scale that you want. You can have an acidic buffer. You could have a basic buffer. You could have a neutral buffer. You will make a buffer at somewhere along that pH scale in the next experiment. So you can make it anywhere along there. What a buffer is a solution that has a specific pH that you make. And then if you decide to add more acid or base to your buffer, it will be able to maintain that pH. It will not have big jumps in pH. So if you added an acid to your buffer, it will not drop way down the pH. It will not drop really big. If you added a base to your buffer, the pH will not skyrocket up from where it's at. It will be able to maintain approximately where it started at. Will the actual pH go up a little bit or go down a little bit when you add an acid or base? The answer is yes. It will go up or down a little bit as you add an acid or base, but you will not get a big giant pH fluctuation when you add acid or base to it. So why does it work, or how does it work to do that? It works to do that by having both of those things in the solution to begin with. So if you made a buffer out of acetic acid and sodium acetate, which is everybody's favorite buffer combo. And you did that, you're going to have that common ion effect that we just talked about. And what's going to happen when you put it into your big beaker, as we've been talking about, it is going to be the weak acid that is basically going to set up an equilibrium. So what happens in that solution is your weak acid will set up your equilibrium, even with the plus sign in there as well, floating around. Now, what happens when you add your sodium acetate in there? This sodium acetate, as we talked about, is a source of sodium and acetate. So when that goes for a swim in there with the acetic acid, what you're essentially doing is kind of beefing up the acetate part of the buffer, right? And what you end up doing is you will now have in this buffer solution two parts to your buffer. You will have an acid part of your buffer, sometimes abbreviated as HA, and you will have a base part of your buffer, sometimes abbreviated as A minus in the lab. So you have both of these things floating around in solution to begin with, and that is crucial for a buffer to be able to work. So why can you not have a buffer that's made up of a strong acid or even a strong base? Let's say you wanted to make the same buffer, not necessarily the same buffer, but you wanted to make a buffer out of acetic hydrochloric acid and sodium chloride. And that definitely is obviously a acid and base combination that are related to each other by 1H plus. The difference though is when you go throw it into your beaker, Your HCl here is a strong acid, which means it's not going to set up an equilibrium. It's just going to frankly fall apart, which means you're going to have floating around there H plus and Cl minus. And now over here, you're adding more Cl minus and some sodium. And what you end up with in this solution is, unfortunately, only the base part of a buffer, right? You don't have the acid part of the buffer, which is kind of an important part to need for it to work. So because it cannot set up an equilibrium, anything that's like a strong acid or a strong base, you will never be able to keep in that buffer solution both the acid part of the buffer and the base part of the buffer. You can only do that with a weak acid or a weak base. Any questions on that there? So how does it actually function to keep the pH from going crazy? Let's take a look at how it actually works, which is we'll start off with a non-buffer solution. And everybody's favorite non-buffer solution is water. Yeah, that is a non-buffer. So if I have myself here a beaker of water, and I decide I want to add some hydrochloric acid to my beaker of water, my hydrochloric acid is going to go for a swim, right? That's going to be a source of H plus and Cl minus. We know that it is again going to pretty much 100% break apart into ions because it's a strong acid. You're going to produce H plus and Cl minus in that particular solution. So you have now just added a bunch of H pluses to this water solution. And maybe you have neutral water. You probably don't, but we'll just call it 7, right? And now your neutral water of 7 is going to now drop very far because we now have a lot of free H pluses in that solution. And since the pH is minus the log of the H plus, and you just added a bunch of H pluses to your water, your concentration of H plus went up and your pH is going to drop a lot in this case. So again, it may go from like a pH of 7 down to like a pH of 2 or something like that, a really big drop in the pH because you just introduced a lot of free H plus very quickly to that solution, causing a very big jump or drop in the pH in that case. Questions on that? Clearly not a buffer because of that situation. If we take our same water solution here and we add sodium hydroxide to it, which is also a strong base, it also is going to break apart into sodium ions and hydroxide ions. And when our sodium hydroxide goes for a little swim here in water, it will break apart completely into, like I said, some sodium ions and hydroxide ions. Now, in this particular case, we're not producing H plus, but more importantly, in this case, we're actually producing a lot of OH minus that's free in the solution. So we got a lot of free OH minus. That's really important because if you remember the relationship between OH minus and H plus is a opposite relationship, which means when you flood that water with OH minus concentration that goes up, the H plus concentration is going to drop a lot. And if the H plus concentration drops a lot, you're then going to see your pH skyrocket upwards, right? Because now you have a lot more OH minus in that solution than you H plus KW, right? So more OH minus and H plus, you're now going to get a pretty basic solution. And again, if your water started at a pH of 7, you're now going to see the pH jump to like maybe 11, 12, or wherever it may end up as it does that. So this is why something like water is not a buffer, because basically we get a lot of H plus very quickly, we get a lot of OH minus really quickly. So how does a buffer handle that influction of those things? So let's take a look at a buffer, and I'm going to use a different one because frankly, I just don't want to write acetic acid times here. So I'm going to use hydrofluoric acid and a little sodium fluoride, the lesser known buffer combination. This is a buffer in this case, and I know this is a buffer because this is a weak acid and this is its conjugate base. This is really the salt of its conjugate base. Now, when we look at sodium fluoride is a salt, which means it is going to really break apart into a sodium ion and a fluoride ion. And the actual buffer parts are these two guys. These are the two real buffer parts here. That is HF, which is a weak acid, and that's his conjugate base there, the F minus. Again, the only difference between those two things, one H plus, right? Our Bronsted-Lowry definition. And that is our buffer in this case. So if I had a buffer solution of this, the hydrofluoric acid is going to set up the equilibrium. I'm going to have H plus and some F minus in that solution. Again, I'm going to kind of beef up the F minus part by adding some sodium fluoride in there as a source of fluoride, and that's going to kind of increase it. Again, here in my buffer solution, I now have the critical parts that I need sitting in that solution. I have my acid part, right? And I have my base part here on my buffer. So now if I decide, hey, I'm going to add my hydrochloric acid to my buffer here. So I'm going to add my hydrochloric acid to my buffer. So my HCl, which again is a source of H plus and Cl minus, I'm going to add in there. When I add the HCl, which is hydrochloric acid, to my buffer, will it react with the HF or the NAF in this case? What should it react with? The reactions are called acid. What type of reactions? Acid and base reactions. So when I add my HCl, which is an acid, they're not called acid-acid reaction because that just sounds funny, right? So when you add that, it should go and react with the base part of the buffer, right? So we get an acid-base type reaction that occurs. So it is going to go find the sodium fluoride and react. It's going to do our classic double displacement reaction, right? Where we switch partners. And we're going to make two things here. We're going to make a little HF and a little sodium chloride in this case, right? There's not any question on that reaction that's going to happen here. So we're going to add this, and it's going to obviously react to our buffer. Now, we made two things here, and these are two important things that we made, perhaps. We made HF, which is actually part of the buffer to begin with, right? Our buffer is made out of HF and sodium fluoride, and we actually made part of the buffer in this reaction. And that always occurs. So when you add acid or base to your buffer, you're actually going to use a little bit of the buffer. In this case, we're going to use some of the sodium fluoride to react with it, but you're going to make the other part of the buffer. Hence why buffers can kind of stay there for a bit because you're kind of making a little bit of part of it as you're using the others. So kind of regenerating part of the buffer when you add it. So clearly that's not going to mess up the pH. And then we have this guy here. Dare I say that is sodium chloride. That is a salt. What type of salt is that? Acidic, basic, neutral. That is a... Not everybody at once. Got a 33 and a third chance there. What is it? It is a neutral salt, right? It is sodium, which is neutral, right? Because it's group 1. And it's chloride, which comes from HCl, which is group 1. And that is neutral as well. So that's clearly not going to screw up the pH, which is kind of good. It is actually in this situation what we don't see here that we did see when we added the HCl to water. What did we see when we added the HCl to water that we do not see here? When we added the HCl to water, we produce what? A bunch of free hydrogens, right? A bunch of them floating around. When we added the HCl to our buffer, no free hydrogens were formed, right? That's really important because we had a certain amount of hydrogens to begin with, which means the concentration of H plus stays relatively constant. And if the H plus concentration stays relatively constant, that means, my friend, the pH will stay relatively constant as well, because you're not getting this big change in the H plus concentration. It's remaining pretty much where it started. Truthfully, maybe not exactly where it started. It's going to change a little bit, but not dramatically like it did in water. Any questions on that? So when we add this in, the H plus, which is usually our problematic guy, is going to go find the F minus, and then it's going to make this, and that's going to tie up the H plus from being free. and now it's tied up and not freely flowing in the solution that will affect the pH. Any questions on that there? Now, if we take our same buffer here, do our picture of our buffer again. A little HF action, the floating arrows in both directions, the H plus and the F minus in this case. And again, we have our base part of the buffer, and we have our acid part of the buffer, right? So acid part and our base part, right? So now let's say we added our sodium hydroxide to this, which obviously our sodium hydroxide source of sodium and hydroxide that's going to go in for a swim. Now, when I add sodium hydroxide to my buffer, it should react with what thing? Sodium hydroxide is a base, which means it should react with the acid. So it's going to react with the acid. We're going to get just a acid-base reaction, which means we're going to make water, right? And we're going to make a salt, which is sodium fluoride in this case, also a double displacement reaction happening, right? So we're just going to switch partners, basically. Now, we made water, which obviously is not going to mess up the pH of this solution. We made some sodium fluoride, which is part of the buffer to begin with. So just like we saw on the other one, here we're using a little of the acid part of the buffer, and now we're going to generate some of the base part of the buffer in this case. That's not going to screw it up. So as you might guess, it is actually what we don't see here that's really important that we saw when we added it to water. When we added the sodium hydroxide to water, we produced a lot of what? Hydroxide, right? And when we add this to our buffer, as I super zoom in on that circle, we have no free hydroxide form. And because we're not forming any new free hydroxide, the concentration of hydroxide stays relatively constant. That means that the H plus concentration will also stay relatively constant because they are tied to each other, right? As one goes up, the other goes down. So if you keep the hydroxide constant, H plus is going to be constant. And that again means our pH will be relatively constant as well. Again, I say relatively constant on both of these because if you were following it with a pH meter and you added acid to your buffer, again, you would see it go down just a little bit. If you add base to your buffer, you would see it go up a little bit. In fact, when you make a buffer, like you are going to make a buffer, uh, in real life, when you make a buffer, you will never get the pH to be exactly what you want. And you could actually add more acid or base to your buffer to dial in your buffer to the exact pH. Because it changes so little and it moves very slowly when you do that, you can literally drop by drop add acid or base and almost dial it into the exact pH you want. And you then would have an exact buffer at the exact pH. And that's because you don't have to worry about big jumps in pH. They're going to move very slowly as they move. So what happens in this case is really the hydroxide goes and reacts with the hydrogen there, going to make water, and that's just going to tie up the hydroxide in this case and not prevent it freely. So the way a buffer is really able to maintain the pH of the solution is because it has both of those components in there, an acid part to the buffer and a base part to the buffer. When you add additional acid or base to your buffer, it's able to prevent the formation of free H plus in the solution when you add acid and prevent the formation of free OH minus in the solution when you add base. Because those H plus and OH minus concentrations don't go crazy and they're tied up basically, that keeps the H plus concentration relatively constant. And that's what keeps the pH from going crazy and jumping around high or low a lot. Any questions on how a buffer works there? Could just add I think at the end of that whole conversation, then I don't know what that means, but I think that's how it works. Now, let's talk a little bit about some other things about a buffer, which is if you're going to make a buffer, a lot of times people will make both a buffer kind of equalish acid part of the buffer and base part of the buffer. And a lot of times they'll start with kind of an equal amount of both. And as we saw there from our conversation, if you have a buffer and you add some acid to it, more acid to it, it is going to react with the base part of the buffer, and dramatically drawn here, not to scale. We will increase the acid part of the buffer in that reaction, and we will decrease the base part of the buffer. And vice versa, if you added some more base to your buffer, it's going to react with the acid part, and we're going to make more of the base part of the buffer. And we're going to use up some of the acid part of the buffer. So there is something known as buffer capacity, which means, let's just say, hypothetically speaking, you're supposed to add 0.1 molar hydrochloric acid, and you saw the bottle of 18 molar and thought, looks like a better number. Let me just add the 18 molar hydrochloric acid. You're going to blow right through your buffer, because your buffer is not going to be able to handle that much H plus coming in a lot, because you don't have a lot of base. Now, let's just say you didn't follow instructions and you just kept adding acid, by the way. Every time I keep adding acid, what happens to my base part of my buffer? Starts to go away, right? So as I keep adding acid, I'm using up more and more of my base part of the buffer. So at some point, you could potentially blow through your buffer. And then if you continue to add acid, you're now adding a bunch of H plus. And at that point, you're going to see your pH change a lot, right? Because you kind of blew through your buffer. Same idea on the other end. If you kept adding base, you're going to kind of blow through the acid part of the buffer. Or if you added too strong of an acid or too strong of a base, you can blow through it. Where does that commonly happen, as we'll talk about? When you do titrations. Yeah, you blow right through your buffer as you keep adding like sodium hydroxide in there. You make a buffer and then you blow right through it. And then you cry because your indicator turned really dark pink, and you go, do I have to do my titration again? And it's a whole situation. But hey, that's the next topic, not this topic. We get there next week. But there's definitely buffer capacity. So what is really available in a buffer is this. It is the moles of your acid part of your buffer and the moles of your base part of the buffer. Those are what you have available to you to react with whatever you're adding. So for example, if you had only like 4 moles of each of your acid part and your base part, and you decided to add like 10 moles of acid to it, you have not enough to react with that. And you're going to have a limiting reagent of your buffer now, and part of your buffer is going to get used up, and it won't be able to maintain or work great as a buffer. So when you make a buffer, you want to think about the concentration of everybody and the concentration of the acids or bases you may be adding, so that you make a buffer that has enough moles of acid and base part of it in the buffer itself to be able to handle whatever you add to it without being basically blown through. How do you know how to make a buffer, what you should make a buffer at? That's our friendly neighborhood Henderson-Hasselbalch equation, right? That is the equation basically for buffers. And again, if it's not a buffer situation, you should not be using the Henderson-Hasselbalch, as we talked about earlier. But we could use this to help us decide. Let's say we made a buffer like this. This is equal concentrations of the acid part and the base part, which means if I put that into my Henderson-Hasselbalch equation and I use an equal amount of base and acid, that is the log of 1. Log of 1 equals 0. Yeah. Which means this relationship here is what you're looking for. You want to choose a weak acid or a weak base that has a pKa value that typically is plus or minus 1 of your desired pH. So for example, if you wanted to make a buffer at a pH of 4.8, acetic acid is a great one because it has a pKa value of 4.74. If you want to make a buffer with a pH of 9.3, acetic acid is a crappy choice because it has a pKa value of 4.74. That's far away from 9.3. You would want something like ammonium, which is 9.25. Yeah, that's a good choice, right? So that's much, much closer to it. So you want to try to find, when you have a list of choices like you will have next week, you want to try to find whichever one has a pKa value closest to your desired pH. Now, remind you that you can make a buffer of acid and acidic, basic, or neutral. So that may require you looking up some weak bases and trying to figure out some pKa values that are close to what you're looking for. So, or you can look at the pKb and do it that direction as well. So you could use the Henderson-Hasselbalch equation to help you kind of decide, what you should choose to make your buffer out of. You can also do a calculation, as we will do, to actually calculate how much you need of it. Any questions on that there? That is how a buffer works. Sounds good. So here's just a graph again, talking about what we've been talking about. Buffers should resist the big changes in pH. Again, here a non-buffer solution, you can see pretty dramatic change in the pH as you add acid to it. All right, which of the following can be buffers? Can the first one be a buffer, second or third? Take a look there. Are all of them? Okay, if we take a look here, first one is similar to the one we just talked about. So hopefully you said yes on this. This is a weak acid, right? And this is the salt of its conjugate base. Once again, here, this is a salt, which means it's K plus and F minus. It is the F minus again in the HF here. That is the buffer components. The HF being our acid component and the F minus being our base component. And that would work. Yeah. How about B? Will B work? KBr and HBr. They are related to each other by 1H plus, so that is a check. HBr is what type of acid? HBr is a strong acid, yeah. So because it's a strong acid, can it be a buffer? It cannot. So because of that, it cannot be a buffer because obviously, as we talked about, HBr has no way to keep HBr in solution, so you would not have an acid part to your buffer that's necessary. Little one that some of you will see next week. Little sodium carbonate and sodium bicarb. Yeah. These guys are related to each other by 1H plus. In case you can't see it, it is actually the carbonate, and the bicarbonate is the buffering part of that. Yeah. By the way, which one would be? This comes from carbonic acid, which is a weak acid, and this would be a buffer component as they are related to each other. Which one would be the acid part here? Yeah, the bicarbonate, the HCO3, right? Because it's got an H to give, right? And the CO3 2 minus would be the base part of that buffer. Yeah. Any questions on that? All right, well, that's stuff to digest.